Today, we're going to look at our world from a totally different perspective. Not with our own eyes, but through the powerful digital eye of a computer. We're going to break down how this technology can actually see, understand, and map our entire planet, all from space. So have you ever wondered about this? When you see a satellite image, to us, it's just a picture. But how does a computer see it? How can it possibly tell the difference between a farm and a forest, or track the exact path of a wildfire, all from hundreds of miles up in the sky? Well, the answer is pretty incredible. It's not about looking at a picture the way we do. It's all about teaching computers to read this hidden language of light and data that's embedded in every single image. The name for this whole process is digital image interpretation, and that's exactly what we're diving into. All right, to really get this, we've got to start small. I mean, incredibly small. We need to look at the most fundamental building block of any digital image out there. And that building block, of course, is the pixel. The best way to think about it is like a giant mosaic made of millions and millions of tiny tiles. Each one of those tiles is a pixel, and each one represents a real, actual patch of ground on Earth. Maybe it's 10 meters by 10 meters. It really is the smallest piece of the puzzle. Now, here's the absolute key to all of this. Every single one of those pixels doesn't just have a color. It has a number stored inside it. We call this its digital number, or DN for short. And all it represents is how bright the energy is that's reflected from that little patch of Earth. For a computer, this number, it's everything. So you have to remember, the computer isn't seeing water or sand. It's just seeing numbers. An object that's dark, like a deep lake, soaks up a lot of sunlight, right? So it reflects very little energy back to the satellite, and it gets a low digital number. On the flip side, something bright, like a sandy beach, bounces a ton of light back up, so it gets a nice high DN. Makes sense, right? Okay, so computers can read brightness. Low numbers for dark stuff, high numbers for bright stuff. Cool. But how does it know a patch of low numbers is a lake and not, say, a freshly paved parking lot? Well, that brings us to the core principle that makes all of this work. It all boils down to this one simple, powerful fact. Think about it. A tree, a building, a patch of soil, a lake, none of them interact with the sun's energy in the exact same way. Each one reflects and absorbs light a little differently than everything else. And this unique pattern of reflection, it has a name. It's called a spectral signature. And honestly, the best way to think about it is like a fingerprint. Every object has one. And here's the really cool part. Satellites have a kind of superpower. They see in light bands we can't, like near infrared. By measuring the brightness across all these different bands, they can build a unique profile for pretty much anything. And these fingerprints can be wildly different. Healthy plants, for example, are basically rock stars at reflecting near-infrared light. That's the stuff our eyes can't even see. Water is the total opposite. It just soaks up most light, which is why its signature is so low. And cities, they're a complete jumble of concrete, asphalt, metal, roofs, so you get a very messy, mixed signature. The computer's job is simply to learn how to recognize all these different patterns. So let's recap. We've got pixels. Each pixel has a number, and a collection of those numbers across different light bands gives us a unique fingerprint, a spectral signature. So how do we go from all that raw data to something useful, like a map that actually says forest here and city there? Let's walk through the process. Generally, it's a four-step workflow. First, you have to do some cleanup on the image, correcting for things like atmospheric haze. Think of it like cleaning a dirty window. Second, you enhance the image to make important features pop. Then it comes the real magic, classification. This is where you use an algorithm to assign every single pixel to a category, water, forest, urban, based on its fingerprint. And finally, and this is super important, you check the computer's homework to see how well it actually did. Now, that classification part, the magic step, can be done in two main ways. The first is called supervised classification. Here, the human analyst acts like a teacher. You draw boxes on the image and tell the computer, see this is a forest, learn its fingerprint. The computer learns, and then goes and finds everything else that matches. The other method is unsupervised. Here, you basically just unleash the computer on the data and say, hey, go find natural groups of pixels that look alike. It creates clusters, and then the human analyst comes in later to label what those clusters actually are. Okay, I know this all sounds a little technical. Pixels, signatures, algorithms, but the so what here is huge. The reason we do all this is because the real-world impact is absolutely massive. Let's take a look at what this digital eye is actually doing for us. Think about a natural disaster. In those situations, speed and safety are everything. This technology lets first responders get a bird's eye view of a massive flood or wildfire almost in real time. They can map the extent of the damage from a safe distance and direct help to where it's needed most, fast. And the sheer scale of it is just mind-boggling. We can monitor the health of crops across millions of acres at once. A farmer can spot stress in their field from a satellite image long before they could ever see it with their own eyes. Then you zoom out, and we're using that exact same idea to track something as vast as deforestation in the Amazon rainforest. And it's not just about farms and forests. It's about our cities. Planners can literally watch our cities grow and change over decades, like a time-lapse movie. They can see where urban sprawl is happening, figure out where new roads are needed. It gives us this objective, data-driven look at how we're shaping our own world. So to bring this all home, let's circle back to where we started. The difference between how we see the world and how a computer does. It really is a whole new perspective. Look, the human eye is amazing. We're brilliant at seeing context, shape, and patterns. But let's be honest, our interpretation is subjective and, for large areas, pretty slow. A computer, on the other hand, is completely objective. It doesn't care about shapes or patterns, only pixel values. It's incredibly fast, it's repeatable, and this is the real game changer. Its output isn't just a pretty picture, it's measurable data. It can tell you exactly how many square kilometers of forest were lost. So when you boil it all down, the key advantages are clear. The digital eye gives us incredible speed, it's objective, and it can handle datasets so massive a human couldn't even begin to process them. It has that superpower of seeing light that's invisible to us, and it turns images into hard numbers. It's not a replacement for human experts, not at all, but it's an unbelievably powerful tool that extends our senses. And all of this leads to one final exciting thought. We've effectively taught computers to read the secret language of our planet. As the sensors get more sensitive and the algorithms get smarter, this digital eye is only going to get sharper. So you have to wonder, what new patterns, what hidden changes, what secrets will our planet reveal to us next?